All right, in this video, we're going to look at the worksheet in our books called Acid-Base Concepts Titrations. This is practice doing basic titrations. If you're looking for something on pH titrations, that's a different topic. So this is the basic stoichiometry type of titration problem. So question one, we have a student who's been asked to standardize a strong base, calcium hydroxide, and I notice right away when I see that formula for calcium hydroxide that there's two hydroxides in the formula. It's a strong base. I know that because a metal bonded to hydroxide is a strong base. She decided to titrate that with a monoprotic primary standard. A primary standard simply means a standard, a chemical, which is pure. So she's using potassium hydrogen iodate, and we know it's monoprotic. Because it's monoprotic, when we write a balanced equation, we'll just represent that as HA. It's an acid with one hydrogen. The actual chemical formula for potassium hydrogen iodate is rather complicated, so we'll just simplify it like that. So part A, write a balanced equation for the reaction. It's an acid neutralizing a base, so it's called a neutralization reaction. So the calcium hydroxide reacts with the monoprotic acid. Now, normally you start balancing an equation after you've written all of your products. But in this case, I'm going to start balancing right now because the strong base has hydroxides and the acid has hydrogens. This is going to be essentially a double replacement reaction, and those hydrogens and hydroxides will create water as a product. But they have to be equal. So if the base here has two hydroxides, but the acid has just one hydrogen, I'm going to fix that by putting a 2 as a coefficient for the acid. So now I have two hydrogens with two hydroxides. That's now balanced. The two hydrogens and two hydroxides will combine, and they're going to give me two waters. Right? So one hydrogen plus one hydroxide makes water. So if you have two hydrogens and two hydroxides, you have two waters. The other product is going to be some type of salt. In this case, it'll be calcium with two of those A's, right? If you look at the balanced equation here, we have two A's. So calcium is a metal, and it's going to have two of these A's attached to it. All right, so by putting the 2 in front of the HA at the beginning, before I wrote the products, it simplified things for me. Now I can see that there's a 1-to-2 ratio in that balanced equation. 1 mole of the strong base requires 2 moles of the acid to neutralize it. That ratio is going to be a unit multiplier. All right, so now we also notice we have the molar mass of the acid given up above as well, right? So we want to use a unit multiplier to find how many moles of acid were used. So let's look at the data table beside us. The person used 0.613 grams of the acid, and they probably dissolved that in some water in a flask. It looks like they put the base, the calcium hydroxide solution, in a buret, and then the buret's initial level was 1.05 milliliters, and after titrating, they finished at 35.41 milliliters. That was the volume to reach the equivalence point of the titration. So to get the moles of acid, we can do that by just taking the mass of acid and its molar mass. So let's do that. We have 0.613 grams of the acid. See if you can pause the video and set up a unit multiplier to convert that to moles. So you want to get rid of your grams and switch to moles. Looking up at the molar mass, 1 mole of this acid was 389.9 grams. So 0.613 divided by 389.9, and we're going to keep 3 digits in our final answer here, 3 significant digits. So we have 0.00157 moles of the acid. Okay, so that's a pretty simple calculation, just converting grams to moles. Now we want to use a unit multiplier to find how many moles of the calcium hydroxide were present? Well, we know how many moles of acid were in the flask, were used in the titration, and we have a balanced equation that tells us 1 mole of the base, the calcium hydroxide, reacts with 2 moles of the acid. So pause the video and see if you can use that information with 1 unit multiplier to convert your moles of acid to moles of calcium hydroxide. All right, so we're going to take 0.00157 moles of the acid, and with 1 multiplier, we'll convert moles of acid to moles of the calcium hydroxide. The numbers for this multiplier are just the coefficients in the balanced equation up above. 1 mole of calcium hydroxide needed 2 moles of acid. So just take your moles of acid and divide by 2. So this time my answer is getting pretty small, so I'm going to put it in scientific notation. 7.86 times 10 to the minus 4 moles of calcium hydroxide were used in the titration. Finally, we want to find the concentration of the calcium hydroxide. Well, we all know that concentration, we have a simple formula for that. It's the moles divided by the volume, right? We have the moles, we just found that. So we have to divide by the volume, and the volume has to be in liters, right? So let's look back up at our data table, and we notice in the data table that the initial level of calcium hydroxide was 1.05 mils, and the final level was 35.41 mils. So in the buret, it fell from 1.05 down to 35.41 to reach the equivalence point, the ending of the titration. Technically, I guess that would be the end point of the titration when they stopped. So to figure out the volume used, we're going to take those numbers and subtract them, right? So let's grab our calculator. 35.41 was the final level, minus 1.05, the initial level. I'm going to put these numbers in the table itself. So that means there was 34.36 milliliters of base used. We already found there was 0.00157 moles of acid, and we found there was 7.86 times 10 to the minus 4 moles of base. Now the volume of the base, we've got it now, but it's in milliliters, right? So we want to convert that to liters. You could use a unit multiplier, or perhaps you just know to convert milliliters to liters, you just divide by 1,000 because there's 1,000 milliliters in a liter. So divide that and you get 0.03436 liters. So now we can take those numbers at the volume in liters and the moles of base, and we can show the concentration calculation. We'll take 7.86 times 10 to the minus 4 moles of the base divided by 0.03436 liters of the base, and we get the concentration of the base. So 7.86 times 10 to the minus 4 divided by 0.03436 gives me a concentration of 0.0229. We can keep 3 significant digits. And you could say moles per liter, or you can just say molarity, right? And that concentration we can put up in our table here, 0.0229 moles per liter. All right, so we did those calculations in a step-by-step fashion, right, because it was broken down for us like that. Sometimes you just want to get a final answer in one step, and so that's what we're going to do in question 2. Pause the video and take a look and see if you can write your own balanced equation for the chemical reaction that's happening here. So we're told that the calcium hydroxide solution that we now know the concentration of, it was used to analyze some hydrochloric acid solution, HCl. 10 milliliters of that acid required 17.16 milliliters of the base, the calcium hydroxide, for neutralization. So the balanced equation would be the reaction between the calcium hydroxide and the hydrochloric acid. It doesn't matter which order you write them. You could put the HCl first if you prefer. And let's try that trick again of balancing before we write the products. So this strong base has 2 hydroxides, and the acid is monoprotic, just like earlier. It's got 1 hydrogen. The hydrogens and the hydroxides in a double replacement reaction are going to make water, but we have 2 hydroxides and only 1 hydrogen. So let's fix that by putting a 2 in front of the acid. Now we have 2 of each. So that's going to create 2 water molecules. And then the other product is some type of salt, and in this case it's calcium chloride. There's 1 calcium, and looking at the left side, there's 2 chlorides. So CaCl2 would be the formula of the product there, calcium chloride. Notice again, it's a 1:2 ratio in that balanced equation. Part B says use a string of 6 unit multipliers to find the concentration of the acid. All right, so we're trying to find concentration of acid. So to do that, we're going to start with the information about the base, right? If we want to know the concentration of the acid, we start with something we know about the base, and then we're going to do some stoichiometry to figure out what we're looking for about the acid. So the base here was the calcium hydroxide, and there's 2 things we know about it. Up in the question, it told us it required 17.16 milliliters. So we know the volume of the base. In the previous question, we calculated the concentration of the base also. It was 0.0229 molarity. So we have the volume and we have a concentration. So if you think about that, if you know a volume and you know a concentration, remember C equals N over V, then you can find moles of the base, right, using those 2 pieces of information. If you know the moles of base, then a balanced equation, we can convert that to moles of acid using stoichiometry. If we know the moles of acid, and look, we also have the volume of acid, moles and volume, hey, we can find the concentration of the acid, which is what we're trying to do here. But rather than do that in a series of steps, let's do it in a series of multipliers. So we're going to start with the base, but do I start with its volume or do I start with its concentration? The answer is to start with the volume, because the milliliters of base, we can convert that to liters. Then we can use the concentration to switch that to moles. So there's our path. So let's start with the volume of the base, 17.16 milliliters of the calcium hydroxide, right? That's the base. So let's see if we can set up these multipliers. So the first thing we'll do is switch the milliliters to liters of calcium hydroxide. Be sure you put the label, not just the unit. And then we can use the concentration that we know to switch the liters to moles of calcium hydroxide. Again, make sure you put the label calcium hydroxide, not just the word, the prefix mole or the abbreviation mole. Now that we have moles of the base, the calcium hydroxide, we can do the stoichiometry. We can use our balanced equation, and we can convert the moles of the calcium hydroxide to moles of the base, of the acid, in this case, hydrochloric acid. Now, once you have moles, you can switch that to a concentration by just dividing by volume, right? If you look back up at our formula, C equals N over V, you just take moles and you divide by volume. So I'll just put a 1 on top and the volume milliliters of the acid, right? We were told 10.00 mils of the acid. But you can't use milliliters. You have to use liters when you're doing a concentration. So the last thing to do would be to switch the milliliters to liters of the acid. And now I think we're good to go. So the first unit multiplier, this is just switching liters to milliliters. 1 liter has 1,000 milliliters. The same thing happens at the very end. There's 1,000 milliliters, 1,000 milliliters in a liter. The second multiplier, if you look at its units, moles per liter, that's the concentration of our calcium hydroxide, moles per liter. We figured that out in the last question. It was I just keep switching to my eraser here. It was 0.0229 moles per liter, right? That was the final answer to question 1. The next one is moles of acid and moles of base. Well, that would be stoichiometry. That comes from the balanced equation. We look at the balanced equation. 1 mole of calcium hydroxide needs 2 moles of acid. And then we just divide by the volume of the acid, which was given in the question. It was 10.00 milliliters of acid. And we're good to go. Grab your calculator. Now, it said use 6 multipliers, 1, 2, 3, 4. We ended up using 5, so I think there's a little mistake there. It should have been 5 multipliers. So 17.16 divided by 1,000 times 0.0229 times 2 divided by 10 and times by 1,000. Now, someone may have noticed that the thousands actually cancel out, and you may have just done that as well. So the concentration of our acid at the end, if you cancel out all of the units here, mils will cancel with milliliters at the beginning, liters with liters, moles of base with moles of base, milliliters of acid with milliliters of acid. And what did we not cancel out at the end? Well, we have moles of acid over liters of acid. That's moles per liter. That's concentration. So this is going to be 0.0786 molarity is the concentration of the acid. Question 3, what does it mean to standardize a solution? Well, actually, that's what we just did in both of the previous questions. We had in question 1 a solution of strong base, and we didn't know what its concentration was at the beginning. So we did a titration reaction, a neutralization reaction with a monoprotic potassium hydrogen iodate, and at the end of that, we figured out the concentration of the base. In part 2, we took the base, whose concentration we now know, and we used it to find the concentration of an unknown acid, the hydrochloric acid. So what does it mean to standardize a solution? It means to determine its concentration, okay, with a high degree of accuracy, right? So not just that it's approximately something, but we have 3 significant digits in our concentration, so we know it quite accurately. Question 4, okay, when you do a titration, you use a piece of glassware in the lab called a buret. The buret is a tall glass tube, and the liquid that you put in it forms a meniscus, right? The meniscus is this curved surface of the liquid, a meniscus. When you read the volume in a buret or in a pipette as well, or in a graduated cylinder, there's always this kind of meniscus. You have to look at eye level. So if you were in the lab, your eye has to be here. Okay? There's your eye looking at eye level. And you have to look at the very bottom of that curved surface. So you look at the bottommost point on the curved surface, and you ask, what is that volume? Now, I'll do this first one with you. Notice that the level of the liquid inside, the bottom of that meniscus, is somewhere between 20 and 21, right? You can look at the top there, 20 and 21. A buret is not the same as a graduated cylinder. It drains liquid out, right? So 20 is above the 21. So it's between 20 and 21. So let's say 20 point something. Then we notice each little tick mark in between the 20 and the 21. If you count them, there's 10 spaces. So that means each one of those little spaces is 0.1 milliliters. Now, sometimes it's easier to count up rather than down. So for example, if you look at the slightly longer tick mark here in the middle, that would be 20.5. Right above it is 20.4. Right above that is 20.3. And above that is 20.2. So the bottom of the meniscus is past 20.2, but it's not yet at 20.3. So it's going to be 20.2 something. And the last thing to do is to estimate how far between 20.2 and 20.3 are we? Are we closer to 20.2? Is it going to be something like 20.22 or 20.23? Or is it closer to 20.3? In which case we'll say 20.28 or 27 or 29. Well, in this case, I would say it's closer to 20.3. So I'm going to be past the halfway point. But it's not like right close to 20.3. So I'm going to say 20.28, maybe 20.27. Either one of those would be okay. And that's milliliters. All right? So now can you do the same thing with the second one? Pause and take a look and see if you can figure out the volume here. So right away we see it's between 22 and 23. So we'll say 22 point something. This time I'll count down from up above. If this is the 22 right across there, that's 22. Then that first tick mark is 22.1, 22.2. It's between 22.1 and 22.2. So it's going to be 22.1 something. I think it's closer to 22.2. So I'll say it ends in a 1, well, I guess I'll go with a 1.8 again, or maybe a 1.9 this time. Okay, 1.8 or 1.9 milliliters. And then the third one, pause and see if you can get that. Okay. This one's more likely a pipette instead of a buret, but it's the same idea. So the level is clearly between 1 and 2, so it's 1 point something. This slightly longer tick mark in the middle is 1.5. The one right above it is 1.4. The level is between 1.4 and 1.5, so it's 1.4 something. It's very close to 1.4, but it's slightly past. So you'd probably want to say here 1.41 or maybe 1.42, something like that, milliliters. All right, so when you're in the lab and you're doing a titration, that's what you have to do. So in question 5, we have a picture of the buret before the initial reading and after at the end of the titration. We're going to need to do what we just did and estimate the volumes in the levels rather in the buret. A student measured out 0.374 grams of a solid triprotic acid. So this acid has 3 hydrogens in it. They dissolved it in some water, 25 mils of water. They then titrated that using, and look at this, a concentration of potassium hydroxide, which is base, right, a strong base. And it says to the 3rd equivalence point. Our acid was triprotic, so it has 3 hydrogens. You can neutralize just the first of its 3 hydrogens, in which case you'd be saying we're going to the 1st equivalence point. You could neutralize 2 of its 3 hydrogens, and then you'd say you're going to the 2nd equivalence point. Or you can neutralize all 3. You can completely neutralize it, and then you're going to the 3rd equivalence point because it had 3 hydrogens in the acid. We're using phenolphthalein as an indicator. Remember, when you do a reaction like this, you're mixing something that looks like water, the acid, with something that looks like water, the base, and you can't see anything when they react. So we use an indicator, in this case phenolphthalein, to show us when we've reached the end point of the titration. When the indicator changes color, we stop mixing the acid and base. So start off by writing a balanced equation. Pause the video and see if you can do that. So the acid here was triprotic, so we write H3A, and the base is just potassium hydroxide. We notice that the acid has 3 hydrogens and the base has 1 hydroxide. We want to make those equal, so I'll put a 3 in front of the KOH, right? We're neutralizing all of the hydrogens here. So that's going to give me 3 water molecules, right? So you have 3 H's and 3 OH's, you'll get 3 waters. And the other product is going to be potassium bonded with this A, the potassium and the conjugate base of our acid. There's 3 potassiums and 1 A. The potassiums are positively charged, so they go first in the formula. 3 of those and 1 of the A. So there's a salt produced along with water. Notice the balanced equations ratio. There's 1 mole of acid for every 3 moles of base. So part B says what volume of the KOH was used. Well, the KOH is potassium hydroxide was in the buret, right? There's a solution of it in the buret. So pause the video and see if you can record for yourself the initial and the final volumes, the initial and final levels. So the initial level is clearly between 9 and 10, so it's 9 point something. And then I'll count backwards. This is the 10 at the bottom, so this would be 9.9, 9.8, 9.7, 9.6. It's between 9.6 and 9.7, so it's 9.6 something. It's closer to 9.6 than to 9.7, but it's not very close to 9.6, so I'll say something like 9.64. I think it's less than halfway. You might have said 9.63. That'd be okay. And that's milliliters. On the other side, at the end of the titration, when they finished titrating, adding the base to the acid in the flask below, they stopped with this level. So let's count again. It's between 24 and 25, so 24 point something. This slightly longer line in the middle would be 24.5. Then this is 0.4, 0.3, 0.2, 0.1. So it's past 24.1, but it's not at 24.2. So it's 24.1 something. And then we'll say it's kind of close to halfway between them, but I don't think it's quite halfway. So I'll go 24.14, maybe 24.13. Okay, these are estimated, those last decimal places, so we could slightly disagree and you wouldn't be wrong. So now that we know the initial and final level, we can calculate the volume used. So 24.14 was our final level minus the starting level, 9.64. Now when you're subtracting numbers like this, your answer should be rounded off to the same number of decimal places that was fewest. So we have 2 decimals and 2 decimals. We're going to keep 2 decimals in this answer. So 14.5 is what my calculator says, but I need 2 decimals, so I'll put a 0 at the end. Right? When you're adding or subtracting measurements, you base your rounding off on the number of decimal places. Now this is the volume of the base, the potassium hydroxide. We know the concentration of the base, right? We were told the concentration was 0.0652 molarity. We know the mass of the acid used as well, okay? Keep that in mind. And we have a balanced equation. Use a string of unit multipliers to find how many moles of acid that were present. See if you can pause and do that. Okay, to find the moles of acid, maybe you were thinking you could just take the mass and go find the moles, but you can't because we don't know the molar mass of the acid. In fact, that's what we're going to find next. So to figure out the moles, we have to do it in a different way, and that's where the titration comes in. We'll start with the base, and once we've got the base, we'll then figure out how many moles of acid we used. So for the base, just like earlier, we'll take its volume as our starting point, 14.50 milliliters of the base, and let's convert the milliliters to liters of the base. And then, because we knew the concentration of the base, we can switch the liters to moles of the base, right? Remember, the concentration was 0.0652 molarity. Then we can use the balanced equation stoichiometry, and we can convert moles of the base, the KOH, to moles of the acid, the H3A. So 1 liter has 1,000 milliliters. The base concentration, 0.0652 moles per liter. And the ratio in my equation says 1 mole of acid needs 3 moles of base. So 14.5 divided by 1,000 times 0.0652 divided by 3, keeping, let's see here, 3 significant digits because of that concentration. We're going to get 3.15 times 10 to the minus 4 moles of our acid. So that's what was in the flask during the titration, that many moles of acid. But we know how many grams of acid we used, right? We know there was 0.374 grams of this acid. So if you know the mass and you know the moles, then you can find molar mass, right? We have a simple little formula that tells us moles is mass divided by the molar mass. If you rearrange that, the molar mass would be the mass divided by the moles. So we'll take our mass, which was up above, 0.374 grams, and we'll divide by the moles. This is the acid we're talking about. The moles was 3.15 times 10 to the minus 4 moles, right? So 0.374 divided by our last answer. This molar mass is quite large. It's 1,000, so we can keep 3 digits. So I'll say 1,190. My calculator says 1,186.7, but I can only keep 3 significant digits. So 1,190 grams per mole. Of course, you could also put that in scientific notation and call it 1.19 times 10 to the 3 grams per mole. All right, the last question here is a conceptual one. What's the difference between an end point and an equivalence point of a titration? Well, let me start with the second one, the equivalence point. I've used that term a few times. The equivalence point is the point in the titration where you should have stopped. Okay, it's where you should have stopped because the acid and base were perfectly neutralized. Right? So in the last question, we were adding base, we were adding potassium hydroxide from the buret to neutralize the acid that was in a flask below it. So the equivalence point was the point in the titration where you should have stopped adding the potassium hydroxide because you had added exactly enough to neutralize the acid in the flask below. So the equivalence point is the point where you should have stopped titrating because the acid and base were exactly neutralized. The end point is the point in the titration where you stopped, okay? It's where you actually stopped titrating. So you can think of it as the equivalence point is where you should have stopped, while the end point is where you actually did stop titrating. Why would you have 2 different terms? Well, remember we said that you're adding something that looks like water to something that looks like water. So you can't see the reaction happen. So it's very hard to tell when you should have stopped titrating, because you can't see the reaction happen. So we rely on that acid-base indicator. We relied on phenolphthalein. We had an acid in the flask down below, so if you recall, phenolphthalein would have been colorless when we put that in the acid. As we added the base, the pH was going up, and so eventually phenolphthalein turned from colorless to pink. And we decided that that point where it changed from colorless to pink would tell us to stop titrating. So we were relying on that color change. And of course, the human eye isn't perfect. We can, is it pink? Is it too dark pink or too light pink? We may have added a bit too much. We may have added not quite enough. So the point where we actually stopped is the end point of the titration. And it's possible we stopped at the wrong point, right? It's possible there was error. So the end point where you actually stopped titrating because there was a color change with your indicator, and the equivalence point where you should have stopped titrating because the acid and base were perfectly neutralized. So I hope that helps understand acid-base titrations, some background, some theory, some practical things like how to read a buret, and how to do calculations involving titration problems.